So the policy function, okay, so all the solution, right? So the solution of this dynamic optimization problem should be just all these control variable, they all depends on AT, okay, as a function of AT, okay? So if you look at this non-linearized system, it turns out that the solution, the policy function, will also be linear. So this non-linearized system, okay, everything linear, and then we are looking for a policy functions that satisfy all these things, right? And then it turns out if you have a linear system like that, the policy function will also be linear in the state variable. Namely, so the solution, they all looks like this. Okay, so they are all linear function of the state variable. Okay, CT is some coefficient, right? Some constant times AP is constant times AP and so on. All of them are linear function. Okay, and then here in this particular case, you can actually use the method of undetermined coefficient to find an analytical solution of these coefficients. Although the computer can find exactly the same answer numerically, but by algebra, we can actually find out exact analytical expression for these coefficients. So the goal here is to find out all these phi, right? Phi CA, phi YA, all these coefficients. So the method undetermined coefficient is that you try to substitute these things into the Euler's equation. For example, so let's say, so you look at the labor market conditions, right? So you look at the labor market condition. Let's say these are labor supply, labor demand, right? Okay, equilibrium should be demand equal to supply. So you can equate these two. Okay, so you have good idea to go through a couple of steps. This is algebraic manipulation. So this, let's say you have demand and supply. You have demand and supply like this. Okay, this is supply, right? Labor supply, and then you have labor demand that follow this relationship. So this is demand, right? And then you say equilibrium. The two things must be the same. So you solve for the equilibrium things. So okay, equate them, okay, and then you substitute the solution. So here we know for this kind of problem, the solution should be all linear function of AP. All these are linear function of AP. So you substitute this thing. So let me systematically call this CA coefficient AP, right? Like that. Okay. And then similarly, you can have sine NA like that for this term. So for this term, and then this thing AP itself. You need to do anything. NA, and then add things like that. Okay. Okay. And then you can see by collecting terms. Okay. They all so you end up with this linear function of AT tilde, and notice that this equation is meant to be true for all possible value of AT tilde. So therefore, the coefficient has to be the same, okay? So the coefficient has to be the same. Otherwise, you can choose some value of A tilde to violate this inequality. So you end up with, so this is meant to be true, right? For all possible values of A tilde. So therefore, the coefficient has to be the same. So you end up with a equation like that, and then you have this NA, right? So you have NA, so you have this one unknown here, the other unknown here. So you have one equation and two unknown. You cannot solve them. So you need another equation. So basically, you go through this kind of process for all your equations. Okay, so you would end up with, so you go through this process. So you go through this process, right? Just like what I show you, you collect time. So you have one equation in two unknown, phi YA, phi NA. So this is not, just this alone cannot solve for these two. And you do use the other equation in your system. You go through this process. Now you see here, you find another equation that has these two unknown, phi YA here, phi NA here. So two linear equations in two unknowns, right? And then you can solve it by algebra. Okay, so you can solve it, and then the solution is phi YA equals this, phi NA equals to that. So this is an analytical solution, which is not possible by computer. Okay? Computer can only give you if you tell the computer what is the value of this parameter, and then it will numerically calculate a number, but you don't have a formula like that, right? Okay, so here you have closed form solution, so you go through this process, and then you can find out all the closed form solution as we show you here. So you will also tell you that, okay, the same results. Now you can see this closed form solution can be quite useful, right, to understand the model. So for example, the closed form solution for work effort, right, for labor supply, okay? So you see here the closed form solution for labor supply is this one, and then you can see it depends the sign of these things. So for example, let's say your phi, remember this phi parameter, it kind of measure the elasticity of labor supply, right? Elasticity of labor supply, 1 over phi. 1 over phi is the elasticity of labor supply, okay? So if you have a large, small phi, let's say, suppose your phi is very, very small, okay? Phi is 0.01 or something like that, very, very small. 1 over phi will be very large, then it means that people are more willing, when they are very willing to work, right? Whenever the wage is just a little bit higher, okay? So they are very, very willing to work, quite elastic in their labor supply. And here, this show up here, high productivity. Let's say your high productivity, right? High productivity means high wage, okay? High productivity, because your wage is marginal product of labor, right? So high TFT should be high wage. And if you have a phi very, very small, means this coefficient is very large. Other things being equal, right? So the response, so then this gives you the closed form solution, right? So that to what extent, so this response of labor supply will be quite large with respect to positive productivity, okay? And also this sigma, so this sigma parameter has to do with the intertemporal substitution, right? Intertemporal substitution of the consumer. Okay, 1 over sigma is the intertemporal substitution. So here, sigma, let's say sigma smaller than 1. Sigma smaller than 1, like a 0.5 or 0.02, whatever, okay? So 1 over sigma will be bigger than 1, quite large, right? Then it means people are willing to tolerate fluctuating intertemporal consumption profile, right? Okay? So in this case then, this thing will be positive. Okay, this thing will be positive. So if there's a current positive productivity shock, people will be, so this optimal decision rule says that people will work very, very hard in response to this positive productivity shock. And then you can understand why. Because they are willing to tolerate fluctuating consumption, right? So that they will try to go for intertemporal substitution. Work very hard now, okay? Work very hard now and then take a rest in the future. Okay. So in this case, if you remember, the in semester 1, the concept is substitution effect dominate. In this case, substitution. Okay. And when sigma is 1, then the two things just cancel out. Substitution effect, income effect will cancel out, and then the NT is actually constant, will not respond to productivity shock. And then let's say here, sigma bigger than 1, sigma bigger than 1. So you will end up with negative here, right? So this term will be negative. Then it says that when there's a positive productivity shock, people tend to work less, right? And from semester A, we understand why, because the income effect dominates, right? Income effect dominates. So in semester 1, we talk about these two concepts, right? So substitution effect and income effect. Right? So if your current TIP is very high, you have a lot of output, then it will generate two effects, right? So on the one hand, it is, so if you work harder, you can produce a lot more output, and this is substitution effect. But on the other hand, because your output is high, then it means that your the wealth is high, and therefore income. In fact, if you assume your leisure is normal goods, so you want to consume more leisure, therefore your labor supply should go down, right? Okay, so then if the substitution effect dominate, then whenever current productivity is high, people want to work harder, right? So here, this will depend, so the size of the substitution effect and the income effect actually depends on people's taste, right? In this case, we show you explicitly, it depends on the extent to which they are willing to substitute consumption intertemporally. Depends on this sigma parameter. Okay, so here, as you can see, so the closed form solution is very useful, right? So you kind of understand the properties. It sort of help you understand the properties. Yeah, so you can, maybe you can take a look at these things. So this is the numerical, not the numerical, but the analytical solution. Okay, so here, so as you can see, obviously this kind of pencil and paper solution is only possible for simple model. Now, even for this case, you don't have capital, right? You only have labor in your production function, you don't have capital, and you have this nice functional form. It's already quite a lot of work. See, by pencil and paper. See, just slightly make your model a little bit more complicated, like taking a more general functional form, you can pretty much forget about it, right? So the analytical solution not possible. But for the computer, quite easy, right? Numerically. So here we show you how to do that, and here notice that this analytical solution, right? So this is just for the real variable, right? So we said that you only have enough equation to determine the real variables, like the work effort, output, consumption, real interest rate, and so on. But what about those nominal things, like the inflation rate, like the nominal interest rate? So here we show you examples. So you need to expand the model. You need to explain where's your money coming from, or how the nominal rate is determined, and so on, right? So one approach is known as the cashless approach. So this approach is that you just assume money, you are not really, so here basically you just add one equation that describes the nominal interest rate directly. So this is the interest rate rule. So the motivation of this is because John Taylor, some years ago, suggests a Taylor rule that describes central bank behavior reasonably well. So the Taylor rule expression. So here, go to the other file, or maybe at the end of this file, you have the numerical example. So the later version, because it's too long, I cut up the file into two, so we can put it just the same. So here, so we take this classical model, right? The same set of equation, but here we explain where this nominal, how this nominal interest rate is determined. Okay, so this is known as the interest rate rule, or the Taylor rule. Okay, so this kind of describe, because nowadays from news and so on, you often heard that, let's say, the central bank, okay, the Federal Reserve Bank is going to keep the interest rate constant, or the central bank is going to raise the interest rate or to lower the interest rate, right? So it seems that the central bank try to control directly the interest rate, right? So this is the idea. So here, this thing try to describe the central bank's monetary policy behavior. Okay? So the central bank manipulate the nominal interest rate. Now, in our model, now, by the way, even though in the news it say the central bank is going to raise the nominal rates by 1% or by 0.5% or whatever, it doesn't really set the interest rate. Because if you look at our model, the interest rate is the reciprocal of the bond price, right? So the central bank, or at least the Fed, or major central bank in the world, they conduct open market operation, buy and sell bonds. Now, if you can push, if you sell a lot of bonds, let's say in the market you sell a lot of bonds, you make the bond price low. This is just the same as raising the interest rate, right? So technically, it's not really set the interest rate, but rather by buying and selling government bonds. Okay? So this is known as open market operation. Now, for some other central bank, I'm not sure this is really the case. For example, the People's Bank of China, they probably set the interest rate directly, in the sense that they set maybe the interbank rate, maybe the discount rate or something like that. Okay, the rate, the interest rate that the central bank lend to the commercial bank. Now, I'm not sure about whether the People's Bank of China do open market operation like the U.S. central bank or not, which I'm not familiar. Okay, but at least for US or Europe or Japan or major central bank in the Western world, the way the central bank so-called set interest rate is open market operation, okay? Which is apparent in our model, right? Because we have the bond and nominal bond, and then the QT is the price of the bond, right? Then by buying and selling, you can. And moreover, the reason why the central bank, if they do open market operation, they can pretty much control the price of the bond at any rate they want, because the major difference between a central bank and a private individual is that, let's say, suppose you want to buy bond, how do you pay for it? You can invest, right? You can put your saving into bond, right? You buy bond, right? You want to pay, you pay money, but where's your money coming from? Must be somehow from your uncle, and your uncle earned the money from working or something, right? You see the central bank, however, when the central bank buy bonds, it can print money to buy bonds, because the central bank can create money, right? So basically, so then it means that they can, if they want the bond price to go up at any level they like, because they can always print more money, right? So this is just the same as printing a lot of money, okay? Then so that's why they can pretty much control, right? So sell bonds, maybe if you have a lot of bonds, then you sell it, right? Okay? And buy, because they can print money to pay for it. So that's why they can pretty much control the interest rate at any rate they want. Okay. So as you can see here, we want to solve the model not just for the real variables, right? And we need all these equations so that we can solve it for the nominal interest rate and also the inflation rate. And here we illustrate, we have two random shocks here. So even this interest rate rule, we assume that it has a random shock. Okay. It doesn't have to be, but try to illustrate, okay? It's not necessary, but I try to illustrate, which is realistic, because you don't expect the central bank by buying and selling bonds, they can exactly get this. Maybe there's some mistake and some variation, right? Some variation, although the mean might be the same, but sometimes a little bit higher, sometimes a little bit lower. So this is captured by this randomness. And also this is a rule, right? So this rule means that the central bank try to manipulate the nominal interest rate according to inflation. So this is known as inflation targeting. Inflation targeting. So here this coefficient 5 pi here is positive. 5 pi positive. Okay. So in the real world, central bank, they tend to adopt this kind of inflation targeting rule. Okay, when the inflation rate is high, let's say when your pi t is high, central bank want to raise the interest rate because this 5 pi is positive. So it kind of describes the central bank behavior. And it turns out that there's a very interesting result. This 5 pi has to be bigger than 1. Okay, so if this 5 pi is bigger than 1, then you will have unique stable solution. The system will have unique stable solution. On the other hand, if your 5 pi is positive but smaller than 1, there will be many solutions. Okay, there will be multiple solutions. And we will call this a sunspot equilibrium. Sunspot equilibrium. So sunspot equilibrium in the sense that there will be solution that satisfy all these Euler's equation, right? So if they satisfy the Euler's equation, then it means that it is utility maximizing, right? So it's profit maximizing and also market clearing, and yet they may exhibit all kinds of behavior. Okay, and in fact, people use this framework to study inflation in the 70s. So if you know something about history, economic history, it's called Paul Volcker experiment or something in the 1980s. So in the 70s, inflation was very, very high all over the world. Okay? In particular, so basically what happened is that people find that if they fit this kind of model to the data, they find that in the 70s, they find that the Fed's phi pi, this coefficient, smaller than 1. Okay, it's positive. See, they always say, okay, whenever there's inflation, the Fed, the central bank want to fight inflation and raise interest rate, but not strong enough. You see, when phi pi is bigger than 1, what is meant by bigger than 1? Then it means that if there's a 1% increase in inflation, you raise nominal interest rate by more than 1, right? By more than 1%. So this is, okay, so by just following the inflation is not good enough. So if you want to make inflation stabilize, okay, so then you need to adopt this Taylor's principle, so this phi pi bigger than 1. So they find that kind of explain why in the 70s, okay, in the late 60s and the 70s, inflation all over the world has been very high and changes quite a lot. Okay, and then after the Paul Volcker in 1980 became Fed chair, he tried to be very aggressive in fighting inflation, and then in the 90s or something, after the development of this concept, this kind of model has been discovered. Nowadays, all the central banks all over the world, they use this kind of rule and make sure they are very aggressive in fighting inflation. And then we also see that inflation has been very low in recent years. Okay, so this model can explain why in the past it was so volatile, but recent years, because of the discovery of this theory, it really make it a lot better. So this rule, right? So nowadays, all the central banks are kind of adopting this kind of rule. So for example, if you go to central bank's website, you can pretty much find this statement. Some of them are quite explicit, some of them are not. But you can, for example, let's say maybe, let's say Bank of England. I think Bank of England is quite explicit about their policy rule. So if you look at, let's say, Bank of England websites, they state quite explicitly what are their rules. Okay, so let me see. So the Bank of England website, and then the monetary policy. So first of all, right, the goal, okay? So the monetary policy is to keep inflation low and stable, low. So it means the phi pi is positive, right? Phi pi is positive. So inflation low, and then let's say, and they actually target inflation. So their target is keeping inflation at 2%. They have a target rate of inflation. Okay. So when inflation is higher than 2%, they want to raise nominal interest rate. If it is below, they want to lower, right? So this target. So the current inflation rate 1.8%. The target is 2%, kind of close. So now their current rate, interest rate, the bank rate 0.75%. Okay, and then for some other central bank, their mandates might be broader, like the I think like the Federal Reserve, they have more than that. So the Bank of England explicitly just say that they target inflation, right? So at least they didn't say they care about the output, but the U.S. central bank, they want both. Federal Reserve. So you go to their website, monetary policy. Let's see these. What are the goals? Okay, let's see here. Monetary policy. Okay. So there are 3 goals. Okay. Okay, so stable price, right? Stable price. Stable price, inflation 0. Maximum employment. And then this moderate long-term interest rate, right? So they have more goals. Okay, so a more general, so let's see here, the yeah, maybe you can, if we don't have time to take a look at this thing, but you can take a look, right? So you can take a look if you're interested. So we have a more general Taylor rule actually. So this is the simplest version. So this one perhaps describes Bank of England, right? Bank of England, they have an explicit policy goal of targeting inflation. You have, I think in the next handout we have a more general version of it. So the chapter 3 handout, let me show you the example. Oops, so how come I don't have it? Chapter 3 not disappear. Sorry about that. And let's see here the what? Yeah, download from the web. And then here is, let's say this chapter 3 handout. We also have we should have just example.